Alhamdulillah, sir. You?
Alhamdulillah, fine. So only 8 students. So you had class before?
No, sir, we didn't. It's
Okay.
first class.
Okay, just let's wait for others to join. In the meantime, let me prepare my document. So can you see the screen?
Yes, sir. Yes, sir.
Okay. So let's begin. So today we'll be learning about some simple classifier actually. So we'll start with this naive Bayesian classifier. So I believe you have heard this term, right? Naive Bayesian classifier? No? Anyway, okay. So far, what we have seen, okay, we have seen a generative model, okay. So we'll be talking about the difference between generative model and discriminative model. Okay, so today we'll be learning about one generative model. So before we do that, okay, first of all, we'll be just getting a definition into probabilistic classification. Okay, so probabilistic classification means that the model that we are using for classification is going to be a probabilistic model. So it's very simple. That means probabilistic classifier, you will use this probabilistic model. And now, what is the probabilistic model actually? The probabilistic model basically gives the probability of a sample, okay, a particular sample, whether it belongs to class 1 or class 2, or let's say if I define it like this, whether it belongs to the positive class or its negative class. And then basically the classifier, okay, at the end, the decision rule, it has to decide, okay, whether the sample, this instance, okay, this instance means basically we are talking about the particular test sample, okay, try it like this. So this is the test sample. So whether this test sample belongs to the positive class, so if I write like this, this is C1 is positive class and negative class is class 0. Okay, but that is a binary classification problem. Since we have used this probabilistic model, okay, that means for each class we get a probability. Let's say if I say like this, okay, there is a 70% chance that it belongs to class 1 and there is a 30% chance that it belongs to class 0, that means the negative class. Then finally, you will have to take the decision, okay, whether you want to classify the test sample to class 1 or class 0. So into which class will you assign it to? of course you will assign it to class 1, right? Because the probability of the probability of being into class 1 is higher than the probability into being to class 0, right? Yes or no? So this
Yes,
is actually what we are going to do, okay? So that means the probabilistic model, okay, they are going to compute the probability of this test sample belonging to either, let's say, class 1, class 0, or if you have more and more classes. So this is actually what you have to do. So that's why I've just shown you the basic steps, okay, the basic steps which is involved in computing the probabilistic model for each class and then taking the decision. So once we take the decision, basically what we have made this probabilistic classifier. Okay, so that means you can see that, say, let's say if you have a number of training examples. So up to now, what I have talked about this test sample. The question is that if I want to compute the probability of being into class 1 or being into class 0, okay, you have to compute it, right? And if you want to compute this probability, you have to basically infer the probability of being into class 1 or class 0. Okay, for that what we have, what we do, we compute. So we take the training examples like we have seen over here. Okay, we'll take these training examples, and normally you will see that often we'll be computing the joint probability of, let's say, class K and the sample X. Okay, this is actually what we are going to compute more often. Once you compute this, from this next what we will do, our goal is to classify an unknown sample. Let's say if I give you an unknown sample, let's say I have given you, this X is unknown, okay, and you have trained your models, all your probabilistic model based on the training sample. This S train means the sample that is coming from the training data set, okay, and then if you have an unknown sample, you want to know, I mean, if you didn't know this probability values at the very beginning, okay, that means from this joint probability, I want to know what is the probability of being to class 1 and class 2. So basically what we have at this particular step, we have this inference stage. And then finally, since I'm building a classifier, so what I have to do, I have to assign the test sample X to the class with the highest probability. Okay, that means basically what we do, we'll compute we'll see that I'll talk about the different terminals later. We'll compute the posterior probability and then we'll assign it to the class with the highest posterior probability. Okay, is this understood? The concept, did you get the concept?
yes,
Okay, that means very simple. So if I say like this, with the training examples, we'll basically build the parameters, or we'll learn the parameters of our models, of our probabilistic model. And once we are going for testing, okay, for the test sample, we have to see with this test sample whether it belongs to class I, let's say whether it belongs to class 1 or whether it belongs to class 0. We'll compute those probabilities and then we'll assign the unknown sample, that means the test sample, to the class with the highest. So you can see over here, there is the argument max. It means that it will assign the sample to the class with the highest probability. Okay, so that's why I have given the definition over here. So now if we talk about this probabilistic classifier, it's a classifier that is able to pick an unknown sample. Okay, this is an unknown sample. Okay, observation of input means unknown sample. What it will do, it will compute a probability distribution of a set of classes that whatever I have said over here. That means we're going to do this inference stage. So this is called the inference. Okay, we're trying to infer. Okay, we're trying to infer the probability of that sample belonging to a particular class, and then we are going to assign it to the one that is most likely. Most likely means basically the one with the highest probability. So this is basically the definition of probabilistic classifier. Okay. So now let's move on. So basically, so far what we have been learning, okay, what we have been from the very beginning, we're talking about this decision theory, okay. So we know that what we do in the decision theory, like the previous one we have talked about, we have used the probability, right? We have calculated the probability. So if you think about from the point of probability, so I've written a lot of text over here. So what does probability gives us? So we know this is a mathematical framework which basically gives us a measure of uncertainty, right? Let's say if I say like this, for class 1 it is 0.7, or let's say class 0 it is 0.3. So are you 100% sure that the sample will go to class 1? Yes or no? No, right? That means you're, like, you can say like this, you're 70% certain that it will go to class 1, but you have some uncertainty in it, okay? Or if you go for this class 0, that means the negative class, that means you're 30%, maybe you're sure that it will go to class 0, but still you have some uncertainty within it, okay? So that's why what the probability value gives us, okay, the probability theory gives us, it gives us a measure of uncertainty. Okay, then once we have this probability value, since we are going to use it to do our decision, okay, to make our decision, so that's why we are moving to this decision theory. That means when combined with probability theory, okay, decision theory allows us to make optimal decision situations involving uncertainty, like this one. If you want to assign this particular sample, okay, you want to assign it to maybe class 0, class 1. So this is the problem of decision theory. What we will try to do, we want to take the decision for this particular unknown sample X. Okay, that is actually what we want to do. So here, we already know about these two problems of decision theory. One is the regression problem, and another is the classification problem. That means if we have an unknown vector X, okay, and then we have this target vector. Target vector means basically in this case, though I have used T over here. So I just took this notation from the book of Christopher Bishop. So I didn't make the change over here. So this one basically is your class. Okay, your class notation. We can say that this is CK. Okay. Okay, in terms of classification, it is class. In case of regression, okay, this is basically the predicted value. Okay, so what we do, so our goal is to predict the value of T, okay, the target value. So target value can be the class value or the regression value, okay, for the unknown sample of X. Okay, so we already know by this time. So this T, that means the target value for regression, is basically a continuous values, and for classification, it's basically some finite value. That means it is the class level, right? So we already know this. Now the thing is that what we need to do, if we particularly focus in the part of this classification. So what we are interested in, as I mentioned earlier, we want to compute the joint probability distribution. That means this term, okay, probability of X and T, or in case of classification, we can specifically say that we want to compute the probability of X. That means the unknown sample X and the particular class, the kth class. Okay. So if we compute this joint probability distribution, what it gives us, okay, it gives us a complete summary of the uncertainties associated with all these variables. So all these variables in this mostly with this particular class indexes, okay. And the problem in this particular case is that the determination of this joint probability distribution from a set of training example is very difficult. Okay, it's very difficult. It's a very difficult problem. And the part where we only estimate, okay, we want to estimate this particular probability value, okay, that is the part where basically we have done this inference stage. Okay, that means once we compute this joint probability, we have got this inference, we have completed this inference stage, and then finally what we'll do, we'll take the decision step. That means the decision step is very easy, the easiest step in decision theory, which tells us that which class we have to assign the unknown sample to, and we already know that whichever is going to be the highest, we'll assign it to that particular class. Okay. So this is the basic theory behind it. So if we just look at an example, okay, let's say in case of cancer classification, okay, let's say X is the features of a patient, okay, let's say X is a vector, okay, remember. So we have extra a lot of feature vectors, let's say X1, X2, let's say we have extra up to n number of feature elements. So we are representing this X as the new patient, okay, the patient, okay. And basically, if you want to know whether this patient, okay, this has cancer, because C1 means, let's say the patient has cancer, and C0 is a negative class, then we can say do not no cancer, or let's say it doesn't have any cancer. Okay, there is no cancer in that patient. Okay? So if we want to assign, let's say if now we have an unknown patient, okay, that means the patient we don't know whether he has cancer or not, but somehow we have extracted the feature values, okay, from the feature extraction. Now we want to see whether, okay, this patient has cancer or not. So which decision are we trying to take? We are trying to compute this probability of having cancer given the sample, or not having cancer given the sample. Okay. So according to the Bayes theorem, okay, we all know about this Bayes theorem. This probability value, the probability of class given sample, can be expressed in the following form, where we have probability of X given class into probability of class divided by probability of X. Okay. So normally what we do, this term, okay, this term, the probability of having cancer or not, regardless of the patient. Okay. So this is normally what we call as the prior probabilities, okay, for each of the classes. Okay. We already know this one. And the probability of X given cancer, that means if you know all the cancer patients, okay, that means you know all the cancer patients, if I say like this, and then I want to see the probability of observing a particular set of feature values. Okay, so if I represent something like this, so this is what we say. This probability term is known as the likelihood probability. Is this understood? Yes or no?
Yes.
Okay, this is the likelihood probability. And then what we see here, so we have one is the likelihood probability over here, one is the prior probability over there. So if you multiply these two terms together, on the left hand side, what we have, normally the left hand side, this probability term is known as the a posteriori, or it is known as the posterior probability. Okay, so if I write like over here, so this is the posterior probability. That means what we try to do, given the sample, that means now we have got the values of x, the feature values of x, but what I don't know whether the patient has cancer or not. So if I want to compute whether he has the cancer has cancer, okay, so I will compute the probability of C1 given x, okay, and if I want to know whether he does not have cancer or not, okay, so I just have to compute the probability of C0 given x. That means x is given, but what is not known, I don't know whether the patient has cancer or whether the patient has cancer or not. Okay, this is the same. Okay? So that's what is known as the posterior probability, and according to the Bayes theorem, we can see that the posterior probability is equal to the likelihood times prior divided by, this is called basically, this is called the, the normalization term. Okay, simply the probability of x. That means we don't worry about this. So how can we compute the probability of x? It's very simple. We can simply compute the probability of x, and let's say if I say like this, for this 2 class problem, we can compute the probability of x into the probability of x and let's say class 1 plus probability of x and class 0. Okay. If we add them two together, we get the probability of x, right? Yes or no?
Yes.
Okay. So this is basic normalization term. Okay. So if we have the training data, now this is the thing. Okay. So for testing, we need this data. Okay. This is needed. But during the training, as we have seen in the previous slide, what do we have to do? So this part is very important over here. Okay. Let's start with this. Okay. We have to compute the joint probability distribution. Okay. That means the probability of x. Okay. Probability of x and class, because this probability basically gives a summary of the uncertainties associated with these variables. So this is what we have mentioned in the previous slide. So that means whenever we are going to have this training data, okay, from this training data, what does it mean? Let's say in case of from the point of supervised classification, that means let's say if I have given you, for example, if I do all these things, let's say if I given you 100 patients, okay, and I know that let's say 70% of them, they don't have any cancer, that means they have no cancer. Okay, so this is the training data. Let's say if I write like this, let's say X train, a sample set. So here I have 100 samples. Okay, 70 of them, they don't have any cancer, and then 30% they do have cancer. Okay, unfortunately. So if this is the case, okay, now what I will do, if I ask you the first term, prior probability, okay, so if I say what is the probability that, like the blind effect, if I ask you what is the probability that there is going to be a cancer patient, what's the probability of class 0?
30.
Oh, sorry, what I say the opposite way, right? C0 means basically no cancer, right? C1 means no cancer. So C0, what's the probability of C0? It's 0.7, right? Yes or no? Okay, it's very simple, right? And then if I say, okay, what's the probability of getting a cancer patient? It's 0.3, right? So then basically we have got our prior probabilities over there. Fine. Now the next thing is that basically we have to look at this likelihood probabilities, right? Okay. Likelihood probability. That means let's say among these 70 patients, okay, among these 70 patients, let's say if I consider only one feature, okay, let's say this is only one feature there. It's only one feature. Let's say this x1 is let's say some blood test, okay? Just say some blood test, okay? So let's say some blood test value, if I write just like this, though it's not, I don't know if clinical it is right or wrong, okay? This is the blood test value here. And then in this direction, okay, we see that, okay, what's the distribution of a particular patient having that particular blood test value. So blood test value may be ranged, let's say from, for example, from let's say 0 to 10, okay? Let's say within this range. The test value ranges from 0 to 10. Okay. Now in this case, we simply want to plot the count. Okay. So if I have 70 patients, okay, if I have plotted them, all of them, or they don't have any cancer. Okay, they don't have any cancer like that. Okay. So what can I do? All these 70 patients, maybe I can have a distribution, and maybe I have something like this. Okay. So that means we know that. I mean, if I add up all the count values, what will the number for this example? Remember, I'm talking, let's say we are talking for this class of C0. So if I add up all the count values, it will add up to 70, right? Because I have 70 samples, or 70 patients which don't have any cancer, right? Yes or no?
Yes, sir.
Okay, fine. Let's say for this particular value of X, having the value of A, let's say if I just draw with a different color, let me draw with a different color. This one, I'm talking particularly for this particular value. So if I say, what is the probability of having this value A, we given the class 0, C0, can you compute this one? It means this particular feature will contain the value A given the class C0. What's the probability? So if I represent like this, first of all, in this class C0, how many samples do we have?
70.
70 of them, right? And we know that this particular count, okay, if I just write like this particular count over here, maybe it has a count of, let's say, n with the value of 8. Yes or no?
Yes, sir.
Okay. Then given the class C0, the probability of the feature value x will have a value of A. That probability value is simply something like this. Yes or no?
Yes, sir.
Okay. So this is the case. You know that all these samples they don't have cancer, and for this particular feature value, we can see the feature distribution. Okay, that particular feature distribution given that particular class, right? Yes or no? Now let's say if I say, okay, what if I have done it for class 1? Okay, the same thing. So let's say we have picked the same feature value x, and then we have this count over there. Okay, and let me pick a different color. Let's say the values again ranging from 0 to 10, and then maybe the patients which have cancer, they have maybe a higher range of values over there. Okay, so similarly, now if I give you all the values, all the training samples, so can you again compute the probability of any value of x given class 0? Oh, sorry, not class 0. Now we are recording class 1. Can we compute that one? Yes or no?
Yes, sir.
Okay, fine. Now, if we have all this information in our hand, now let's say I have given you a test sample. Now, what I'm going to give you, I'm going to give you a test sample. Okay. They say the test sample is saying that now we have an unknown sample x. This is totally unknown. Remember, this is test. The value of x is equal to, let's say, some value. Let's say some value of c. Okay, let me see. Let's some value. Let's say v. Okay, it has some value. So just simply say, okay, we are having x. Now we already get the value of x. Now what is unknown? If we are to do this classification, what is unknown here? We don't know whether it should belong to class 0 or class 1, right? These two things are unknown. Yes or no?
Yes.
Okay, then what can we do? The simplest thing we could have done, okay, if we just simply forget about this base theorem now, we could have computed the probability of this particular value of x having the value of v given class 1, and also we could have computed the probability of this value x equal to v given class 0, right? This is what we could have done, right? Yes or no?
Yes.
And then we could have seen whether the likelihood being to class 1 or the likelihood of being into class 0, whichever is highest, we could have assigned to that particular class, right? Yes or no?
Yes.
Okay. But in this case, we have assumed that both of the class, they have equal probabilities, right? But do you think both of the class they have equal probabilities? Yes or no? Let's say cancer class and not cancer class, do they have the same probability? No. So which one has a higher probability of happening? No, cancer. Okay, fine. So what we'll do, so again, since if we consider these together, we assume both of them are equally likely. Okay, if I write like this, they are equally likely. Okay, but of course it is not true. Of course this is not true. So what we can do for this, what we are going to do, we are going to multiply. Okay, for class 1, what's the probability of being in class 1? One, 3. So we multiply with the prior probabilities of class 1. What's the being into class 0 or the negative class? 0.7. That means basically what we have done, if I just write mathematically, what I have done, we have multiplied with the probability of class 1 for this part, and for that part, see if I write over here, this is or other part we have write the prior probability of class of 0. So isn't it the same thing that we have what we have seen over here? Yes or no? And then if you, since we have multiplied two probability values, okay, so and we know that the left hand side, the posterior probability value, it has, I mean, they should add up to 1. So this is what we have to do. We have to do this normalization, right? Yes or no? So think that this is simply a normalization term. So at the end, if we simply look at the numerator, okay, if you look at the numerator, or if I just look at over here, okay, so let me remove all the things because I believe you understood what I have done. So if I look at the numerator, what in numerator, what do we have? This is the probability of x and what? Class CK, right? Yes or no?
Yes, sir.
Yeah. That means basically you can see that it doesn't matter whether you are doing it for, let's say, class 1 or class 0. The denominator, okay, is same for class 1 or class 0, right? So that means basically if the joint probability distribution, okay, so this is basically what we can see. This is proportional to what we can do in that, right? Like this. The prior probabilities, if we are not worrying about the actual probability term, rather we want to compare. Remember, if we are to compare, like we have done over here. If we compare C0, class C0 or class C0, C1 or C0, that is the positive class and negative class, what we can do to compute the posterior probability, we can only consider the joint probability distribution. Is this understood? Yes or no? Okay. So the thing is that if we have computed the posterior probability, that means the probability of class given x is equal to the joint probability distribution, that means the probability of x and class divided by probability of x, right? That is the normalization term. It's also called the evidence. In some books, it is also called evidence. Okay? It's a normalization term, simple like that one. Now, if I have to compare, let's say if I want to do it for class, let's say if I write it over here, let's say for class 1, the positive class, okay? If I would compute the positive class, I could have checked probability of, let's say, x given class 1 into probability of class 1. And of course, I had to divide it with probability of x. If I had done it for the negative class, that is class 0, I would have computed probability of x given C0, probability of C0 divided by probability of x. Okay? This is the actual value. Now, you want to compare which one is higher, like whether it is like this, whether the probability of being into class 0 is higher than the probability of being into class 1, or maybe the other way around, right? So if you are comparing, the denominator, does it matter?
No, sir.
No. Since we are comparing, that's what I'm saying, that you see that sometimes you see that you may have omitted the denominator terms, because we know that if the left hand side is higher, okay, if we divide from the both sides or multiply with the same value, whichever is higher will remain higher, right? Yes or no? That's why sometimes, since we're doing this comparison, okay, okay, that's why you will see that this normalization term we will omit. Okay, since we have omitted, like I've shown over here, okay, in just at the bottom. Okay, So it should have gone the joint probability distribution, probability of x and class that we have seen over here. Okay, so this whole term, okay, this posterior probability term can be simply written as the joint probability of x and class. Understood? Yes or no? Is a question? Did I answer to your question? Which one? Yeah. Okay. The thing is that if you purely want to look at them as probability values, then of course you have to divide it by probability of x, right? Yes or no? But in case of our particular problem that we have picked over here, what are we doing actually? We want to assign the unknown sample to the class which will have the maximum posterior probability. Yes or no? Okay, so if you want to compare, I assign to maximum class. Okay, so as I said, so if even if I omit this this normalization term, this evidence term or this normalization term, whichever was higher will be still higher. Yes or no? Yeah, definitely we can take the decision. Okay, that's why since we're taking the decision, since we have to compute a value, okay, we have to compute a value, so you can just simply omit this and compute the value and see which one is higher. You don't exactly have to see the exact probability value. Rather, we are looking here which one is higher. Got it? But as I said, if you want to exactly look them as probability terms, of course, then we have to divide it by the evidence probability of x. Okay? So basically what we have done, so this part, so if I remove all the things, this part what we have done, we simply have done this inference stage. Okay, this is the inference stage where we computed a measure of uncertainty or certainty, if you say like this. And the last part, as I mentioned over here, we take the decision. So let's say if I want to give treatment to the patient, okay, so let's say if a patient has cancer, you will give him one kind of treatment. If the patient does not have cancer, you give him another kind of treatment, right? So to minimize the chance of giving him the wrong medication, okay. So you assign, you label the patient as having cancer or not based on this particular posterior probability, right? Yes or no? Let's say if the posterior probability of being into class 1, but having cancer is something like, let's say, 0.2, and not having cancer has a probability of 0.8. I'm purely talking from the point of probability values. Then what you'll do? The doctor will take the decision. Okay, the patient does not have cancer. Okay, give him the treatment with the patient doesn't have a cancer, right? Yes or no? Okay. So even in this case, if I say like that, how much error will you have? What are the chances of having an error here? Can you hear that the decisions I have taken, still there's going to might be a 20% chance that I have made a mistake over here, right? Yes or no? But still what you have to do? You have to make your guess, right? Whether you will go for the treatment for cancer patient or not cancer patient, okay? So based on all the observations, you're basically computing the possibility of this patient, whether he has cancer or not, and accordingly you give the treatment, right? So this is what we do every day in our life. We always make a decision. Like whenever you took a decision, whether you want to study in computer science engineering or whether you want to study electrical engineering, you had to compute a possibility, right? Which one will be better, right? Whether electrical will be better, or whether CSE will be better, or whether mechanical will be better. You have to take a chance, right? Yes or no? And then at the end of your calculation, I believe all of you, at the end of your calculation, studying in CSE, it had higher probabilities, right? Yes or no? So nobody is answering. I know. Did you take the other way? Did you take the decision the other way around? Yes or no? Anyway, anyway, so let's move on. So basically, all this talk, all this talk I just told you, just to come to this particular slide. Okay, the approaches we'll see in solving decision problems. Okay. Basically, as we have seen in this decision tree, we have seen two distinct stages. One is the inference stage, where we'll use the training data. Okay, we use the training data to learn this particular model, probability of x given x, probability of class given x. Okay, that is the posterior probability. And the subsequent stage is the decision stage, where we'll use this posterior probability to make optimal class assignments for the test data. Okay, and basically there are two approaches. Mainly there are two approaches. The first one is known as the generative approach or generative model. The second one is the discriminative model. Okay, in case of the generative model, you see that we'll try to compute the joint probability distribution, probability of x and class, and from here we'll compute the probability of class given x. Okay? In case of the discriminative model, you see that we directly will jump to the conclusion of probability of class given x. So this is where we'll directly jump to this conclusion. We want to compute these values. We don't want to wait to compute the joint probability distribution, or maybe sometimes we'll compute the likelihood probability, because we know that. Let me write like this. Okay, if we compute the likelihood probability of x given class, from here we can compute the joint probability distribution, right? Probability of x and class, and then from here we can compute the probability of class given x. So that means intermediate probabilities we have computed. So if we compute the intermediate probabilities, that model is known as the generative model. And if we directly conclude with the posterior probability, that model is known as the discriminative model. Now, if I ask you, so far, did you see a discriminative model in this course? Yes or no? Did you see a discriminative model?
So in logistic regression, didn't we use something like this?
Okay, and since we're talking about classification, can you give me an example from classification? Okay, it's very simple. Up to this, in case of classification, how many algorithms have we learned? Two, right? We have talked about discriminant function, and also we have talked about this neural network. Yes or no? Right? So let's say in case of a, let's say if I talk like this, in case of a binary classification problem, the last node, okay, the last layer, output layer, this is the output layer. So since you have used the sigmoid function, the result always came within the range of what? 0 to 1? Yes or no? Right? And then basically whatever the value we have got, that value basically gave us the probability of being into the positive class. Yes or no? Okay, so if I write like this, y equal to 1, I should pick a different color. Given x, yes or no? Okay, so let's say if this output was, let's say, something like 0.7, automatically it meant that the probability of the class being into class 0, the negative class, given x was equal to what? 0.3. So didn't it give you some sort of probabilistic value to assign in which class? Yes or no? Okay, fine. That means directly it gave you the probability of class given x. But did you compute any other like probabilities, like the joint probabilities or the likelihood probabilities? Did you compute in case of neural network? Yes or no? No. So that's why the neural network is an example of discriminative model, where you have jumped where you get to compute the posterior probabilities. Understood? Yes or no? Okay. Then there's an alternative approach. It's kind of alternative actually, or much more simpler actually in this particular case, is to solve both problems together. Okay, you can see that we simply because in case of these two stages, okay, in these two models, you have to follow this two-stage approach. Okay, that means you have to do this inference stage, then you have to go for decision-making stage. Okay, there's an alternative step where basically what we do, we directly we take the decision. Okay, there is no inference stage, nothing like that. What we do, we directly take the input and get the decision. Okay, such approach is normally as a discriminant function. Okay, so did we see it? Yes, we have seen this one. Like I've said before, let's say in case of this problem, okay, in the 2D feature space problem, let's if I take the decision boundary like this one. Okay, let's say this is a feature x1, this is the feature x2. Now, if we have a decision boundary, on this side we have the positive region of the class, and on this side we have the negative region of the class. Okay, then we know that this is the equation of a line. The equation of a line is something like, let's say if I write like this, w1 x1 plus w2 x2 plus w0 equal to 0, right? This is what we are seeing as the decision boundary. Now, let's say if I give you an unknown sample over here, this is x. Then this sample x, where will you assign it to? The positive class or the negative class? Positive class, right? Okay, why did we do it positive class? Because we knew beforehand, we have learned before that we have defined a function which is known as the discriminant function, which will define something like this: g of x is equal to w1 x1 plus w2 x2 plus w0. And then if I put the value of x in this function will either return a positive value, a 0 value, or it will return you a negative value. So that means if the function gives you positive, that means it means which class? Positive class. If the sample was over here for this particular value of x, this function would have returned you which value? Negative, that means it belongs to the negative class. And if somehow you had a sample exactly lying on the decision boundary, then the function would have returned you a value of what? A value of 0. That means you are exactly lying on the decision boundary. So in this particular case, did you compute your probability terms? Yes or no? No. And then, but did you take the decision? Yes. So that's why what they are saying is that what we do here is a discriminant function. We simply learn a function that will map the input x to the decisions that we have seen over here. Is this understood? Yes or no? Okay. So what time is it? Too much time actually. Okay, I just want to move directly to naive Bayesian classifier because one of the group you have lab today, right? I just want to go directly to naive Bayesian classifier. Otherwise, you will be really having a problem with the lecture. Okay. Can you see the screen? Can you see my screen? Yes?
Yes, sir.
Okay, so we'll be talking about this naive Bayesian classifier, okay? That is naive Bayesian classifier, okay? What this naive Bayesian classifier does, okay? Okay, say, first of all, it's a probabilistic model because we're going to use the probabilistic computation over there. Second thing is that it's a generative model. Okay, so if I talk about this generative model now, what does it mean? It means that basically we are going to compute either the joint probability distribution or the likelihood probabilities, right? Okay, but this classifier is known as naive classifier because it has a strong assumption that the features will be taken. I've talked about like this. Let's say we have a feature vector of, let's say, x1, x2 up to xn. All of these features, what they assume that all these features are independent from each other. Okay, so this is a very naive assumption or strong assumption. Sometimes they say. Okay, that means we'll assume independence between the features. So, do you think it will be applicable for all cases? Yes or no? No, right? But the thing is that due to this assumption, okay, the night vision model is very simple, and also it is applicable for very large data set. Okay, so that's why sometimes we'll see that though it is very simple and it is a very strong assumption that feature elements will be independent of each other. Okay, so sometimes in night vision classifier we see that it can even sometimes outperform other strong classifiers. Okay? So let's see how it works. Okay, first of all, we know that it's a generative model. Okay, it's a generative model. That what do we want to calculate? Can you tell me? So we have seen that in order to compute the posterior probability, we have to compute the likelihood. We have to take into consideration the prior, and these two terms together will give us the probability of, let's say, class and x. Okay, and divided by this normalization probability of x. For the time being, let's omit this term. Okay. So since it's a generative model, I have to compute what? I have to compute the joint probability distribution. Okay, this is actually what I'm going to compute. Okay, you see over here. Okay, now you see that sometimes if I write only with x, it means that the feature vector x, and if I write with the elements x1, x2 up to xn, that means that basically that feature vector has n different feature elements starting from x1 to xn, and we have this assumption, as I've said before, that those variables or those feature elements are going to be independent of each other. Okay, as I've said here, we are only interested in numerator. Since we're only interested in numerator, basically what we are looking at. So this thing, if I elaborate here, that basically I have to compute the probability of class, the kth class, and the feature values of x1, x2 up to xn. Now, according to probability theories, okay, we know that if I write the probability of A and B, how can we write it? We normally, according to Bayes theorem, we can write that this is equal to probability of A given B into probability of B, right? Yes or no? Now you can see that here we have this term, probability of A given B. If A and B are independent, how can we write it? How do we write it? Hello? Can you hear me? Simply we can write this is equal to probability of A. And then we have this other term on the right hand side, so this is probability of B. That means if I want to write probability of A and B, we can simply write probability of A into probability of B. Now, we have seen that, okay, I want to compute the probability of class given X. I'm going to drop the notation K over here. Okay, and then this one was equal to probability of sample X given class into probability of class, right? Yes or no? Now, if I look at this particular side over this side, so we know that this is equal to probability of the elements are basically x1 and x2 up to xn, given what? Given class C, right? Yes or no? Fine. So this is where we'll start with. Okay. So this is where we will start with. So if this is like this, so remember I have took this probability of C outside. Now basically we are left with probability of x given x2 up to xn given class Cn. Okay. Now whatever we have done here, can I write like this? This is equal to probability of can I write like this? Probability of x1, okay, probability of x1 given x2, x3 up to xn and c. Can I write like this? And what is left? Multiplied by probability of x2, x3 up to xn. Oh, sorry, I just yes. Given class. Can I write like this? Yes or no? Yes or no?
Sir, could you please explain again?
Okay. Okay, let me make it more simple then. Okay, like I can do it over here. Make it latest, let's make it more simple. Let's start with something like this. First of all, We want to compute the posterior probability of class given x. This one I can write as probability of x given class into probability of class, right? Or together this is basically probability of x and c, right? Yes or no?
Yes, sir.
Okay, fine. Red is very odd looking. It should be green over here. Okay. This one, so this x is a vector. So if I break it into its elements, so I can write probability of x1, x2, x3 up to xn and c. Can I write like that? Yes or no? Okay, simple. Then this one I can write like this. The probability of x1, you see, whatever I do like this. Let's consider A is x1 and B is the rest of the terms. Okay, B is whatever I can write x2, x3 up to xn and c. Think like this. So I can write it like this. This is going to be probability of x given x2, x3 up to xn and also c multiplied by what? Multiplied by what? Probability of b? Yes or no? So probability of b means what? Probability of x2, x3 up to xn and c. Yes or no? That means I have notating a as x1 only and b as x2, x3, xn and c. So this probability of a and b, can I write it? So if I write the blue term here, so this is as a and b over here. I'm writing probability of a given b into probability of b. Is it okay? Yes or no?
Yes, sir.
No. This is the simpler Bayes theorem that we have used over here. According to the Bayes theorem, we have said the probability of a and b is going to be probability of a given b into probability of b, right? Yes or no? Okay, but the next thing is going to be interesting over here. But we say that feature A has nothing to do with feature B. They are independent of each other. Then what do we write? Probability of A into probability of B? Yes or no? Is it understood? So if this is true, okay, if this is true, let me remove like that. If this is true, now the next equation, I'm coming from here to there, okay? Then the probability of x1, does it has anything to do with x2? Yes or no? Because we have assumed that they're independent, right? So x1 is independent of x2, it is independent of x3, it is independent of xn, but it is only dependent on which one? Only the class. So this whole term, okay, just remove this one. This whole thing I can write as probability of x1 given class. Yes or no? Okay, because we have assumed independence. That this is actually what the name Bayesian class is. And then we have these other terms. What is the other term? The other term is probability of x2 and x3 up to xn given class. Now we have this. Now if I can I break it again like this? So this is going to be probability of x1 given class. So we are done with this term. This whole term, can we do it like this? This is going to be probability of x2 given x3, x4 up to xn and c. Can I write like that? What is missing? Still something else is missing. So this one multiplied by probability of x3, x4 up to xn and c. Can I write like that? Again, what we have seen over here. Now let's pick another color. Again, this whole term, I have seen that x2 has nothing to do with x3, x4, xn. So this one I can simplify to what? So previously we had probability of x1 given c. Then this red term, okay, this red term I can write the probability of x2 given class. Can I write like that? Yes or no? And then the other term will be there, no problem. So we have probability of x3, x4 up to xn and c. So now we can see that these terms I can go repeatedly like that. What? I can write it like probability of x1 given c, x2 given class, x3 given class, x4 given class, x5 given class, xn given class multiplied by probability of class. Yes or no? Okay, so if I remove like this, so at the end, you will see that this term, probability of x1, x2 up to xn and c, this whole thing can be written as if probability of x1 given class, probability of x2 given class, like dot 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 dot, probability, this is all multiplication, right? Probability of xn given class, and then finally what we have, probability of class. Can I write like that? Okay. And then if this is the case, so since that these are all multiplications, so you can see that the multiplication symbol will be written like this: multiplication of probability of xi given class from I equal to 1 to n, and we had this term probability of c, the prior probabilities, so we can simply write at the very beginning probability of class. Can you, do we get it over here? Yes or no? So this is what we have got over here. And all these terms we have been computing for which one? So this was simply probability of x and c, right? Yes or no? Right? Now, what are we interested in computing? We had computed, if I write it over here, we are interested in probability of class given x. That is exactly what we are computing. And this is equal to, as I have seen before, this is equal to probability of x and class divided by probability of x. This is what we have seen before. So if I simply forget about this denominator, so I'm just talking about probability of x given class, and this is what we have seen over here, right? Yes or no? So that's why you can see at the very end, okay, you had computed the probability, the posterior probability. This is what we had looked at, the posterior probability at the end. The posterior probability, you can see this is proportional sign because we have omitted this normalization. Because if I just simply omit this one, you will see that, sorry, you say this is will be written as proportionate, right? Yes or no? Okay, at the end, so this is a joint probability. As I've said, if I write this equivalence symbol, okay, this means the equivalence symbol. This is the probability of, let's say, class, for the kth class, if I say like this, given x, because I've considered the whole thing as a vector, so I've given x over there. And whatever you have seen over here, like breaking them down one after another, okay, using this chain rule, whatever the chain rule you have seen over there, you ended up having the product of the feature element given that particular class multiplied by what? The probability of that class. So this is basically the equation that we'll be using whenever we will compute the probability of belonging to any particular kth class. It means probability of, let's say, class 0, class 1, class 2, class 3, and so on. Is this understood? And what was the basic assumption here? If I repeat it again, all the features, because since we have assumed they're independent, that's why what we have done, if I remove all this term just to show you again, that's why we have probability of, though we had x1 given x2, x3 up to xn, okay, also c was there. So though this feature we had to compute the probability given x2, x3, xn and c, but since we have assumed independence between features, that's why we have simplified it to what? Probability of x1 given class only, because we know that feature is also dependent on class. This is only where he is dependent. And all these other features we're assuming, okay? Let me write it. Assume not dependent, okay? Is it clear? And this is actually how we break down this whole joint probability into some small conditional probabilities. Okay, conditional probability means, let's say we have written over here probability of x1 given class, probability of x2 given class, probability of x3 given class. So these are some small conditional probabilities, right? Conditional means they are dependent on what? The class we are picking. Okay, so I haven't written which class, so you can write C, we can write as CK.
Yes, sir.
Okay. So you will one group. So today, which group has left? 2B or 2A?
Sir, 2B.
2B. Yes. So we'll see what in this case. I will talk about this. Maybe hopefully we'll do an experiment on sentiment analysis. Okay, from a word we try to judge the sentiment in the particular sentence. Okay. So we'll see that how we convert a sentence to a bag of words, and then from bag of words we'll try to compute the individual probabilities of the word given the particular mood. Okay? So we'll see that, don't worry. So any questions up to now? No? Okay. So we are going to have a class test next week. Just think of when you want to give the class test, okay? So I will discuss about that in the next class tomorrow. Okay?
So what will be the syllabus?
Just think among yourself, okay? So hopefully the rest of neural network, okay?
Okay, sir.
So I have given you the link to your attendance. Have you got it?
Yes, sir.
Okay. So this is it. So hopefully we'll meet tomorrow, inshallah. Thank you. Walaikum assalam.